In lesson 6.10, we're going to divide polynomials. And you might think, wait a minute, haven't we already done this when we used rules for exponents? And we did. We had fractions, and fractions indicate division, but we had a monomial on the numerator and a monomial in the denominator. And of course that means we don't have any addition or subtraction, we only have multiplication and division. And to do that, what we did was we thought about the number part of this fraction multiplied by the fraction with just a base of s, like s over s to the 6th power, and then multiplied by t over t to the 5th power. And then each of those little fractions we could simplify. 4 divided by 2 is 2. If we had s divided by s to the 6th, that's s to the 1st power. So we have one factor of s on the top that's going to cancel one of those factors of s on the bottom and leave us no factors of s on the top. So just a 1 and then s to the 5th power on the bottom. Same thing happens with our t, so we end up with 1 in the numerator and t to the 4th power, only 4 factors of t left in the denominator. Now we squish all that multiplication back together, multiply the numerators, 2 times 1 times 1 is 2, and this denominator of 1 times s to the 5th times s to the 4th just leaves s to the 5th times t to the 4th. And that's our answer. And that is division. But we want to be able to look at dividing polynomials where we have not just factors, but things added and subtracted, so terms. Let's go back to an area model. If we add up the terms for this area model, we see we have 2x squares in blue. If we count the green x's, we have 8 of them altogether. So we're going to add to our 2x squares 8x and then 6 units, so plus 6. Let's say we want to take that expression and we want to divide it by 2. We can write it this way, or we could write that as a fraction, and you'll see it both ways. They mean the same thing. Now if I'm just dividing by a number or just a monomial, then I can take each of my terms and divide each term by 2. Let's look at that for the area model, and I'm just going to draw the model for you. Since I'm dividing by 2, I want to take the components of this area model and divide it into 2 groups. So one group here and another group down here. I need the same thing in each group. That's what division is. So if I take my 2x squares, I need an x squared in one group, and then I also need an x squared in the other group. Now I look at my x's, and I have 8 of them. I want to divide those 8 x's into 2 groups. If I divide 8 by 2, that means I'm going to have 4 x's, which are the green rectangles, in each group. 4 in this group, and 4 in the other group is dividing my 8 x's into the 2 groups. Now do the same thing with the units. I start with 6 units and I want to divide them into 2 groups, so I'm going to put half of those units in the first group, which is 3 units, and the other half, which is 3 units, in the second group. Now I have the original model divided into 2 groups, and I can see what my answer is. Each of these groups represents 1x squared plus 4x's plus 3. And that's the answer I get when I divide that original polynomial by the number 2. You might have noticed that what I could have done symbolically was just take each term and divide it by 2. So 2x squared divided by 2 plus 8x divided by 2 plus 6 divided by 2. Then I could simplify each of the terms. The reason that works is that 2 is a common denominator for each of those terms. If I simplify this, 2 over 2 is 1, so I'm left with 1x squared. 8 divided by 2 is 4, so I have 4 x's, and 6 divided by 2 is 3. And that's exactly what we got when we did the modeling. Models are a great way to visualize things, but they break down when our problems get more complicated. What if I want to take that same trinomial 2x squared plus 8x plus 6, but instead of dividing by 2, I want to divide by 2x. Well, I don't know how many groups 2x is, so I can't model that. But I can use the process that I saw above, and I can divide each term by 2x. So I'm going to take 2x squared divided by 2x plus 8x divided by 2x plus 6 divided by 2x. And then I'm going to simplify each of those fractions. These 2's will cancel. X squared divided by x is just x, plus 8 divided by 2 is 4, and these x's cancel as a factor of 1. And then in the last term, the 6 divided by 2 is a 3 in the numerator. I don't have anything to cancel the x in the denominator, so it stays down there by itself. Let's look at another structure that you might see when you're dividing polynomials. In this case, I have d squared minus 4d that's divided by a binomial d minus 4. So we're dividing by more than one term. When we multiplied things together, we used a box to organize our work. And we had the factors on the outside of the box, and then we added up all the terms on the inside. When we're dividing, we're doing the opposite of multiplication. So the first thing that you see in your division problem is what is filling in the box. And then the second thing, the thing you're dividing by, is one of the factors that goes on the outside of the box. So we're going to put our d minus 4 down the side, and we want to fill in this box as best we can with d squared minus 4d. We have to start with just the first term, which is d squared. We know that needs to go in this first box. Now we can ask ourselves, what do we multiply by d? So what goes in this space above the d squared and gets multiplied by d to get d squared? And the only thing possible is d. So d times d is d squared. Now we also have to multiply that d times the negative 4, which gives us negative 4d. Let's compare that to our original expression right here. We had d squared minus 4d, and that's exactly what's in our box. So our division is complete, and this is our quotient. In other words, that's our answer. So we would say that is equal to d. Now another way that you see division problems would be d squared minus 4d divided by, using a fraction bar, d minus 4. So even though that's written in a different way, it would still divide and simplify to d. Look at the next example. The more terms we have, the bigger our box is going to be. We also have to make sure that our terms are in order with the largest exponent first and then counting down from there. So I'm going to rearrange the terms in this first expression. I need to take the sign that's in front of the term with it. So I'm going to write the negative d squared first, then the minus 5d, and then the plus 41. And I'm going to go ahead and write this as a fraction, although you don't have to do that. These expressions are exactly the same thing. So let's use our box. And I'm not sure how big it's going to be, so I'm just going to draw the first column and leave some extra space to the right. The thing on the bottom of your fraction, I usually like to put that down the side of the box. I know that this is one of my factors, and then the factor that I get across the top of my box is actually going to be the answer to my question. So I'm going to start filling in the box with the first term. I need negative d squared in the first box. So I know I have to multiply negative d times d to get that. Now multiply negative d times negative 5, and that's a positive 5d. Notice that the second term in my numerator is negative 5d. Well, negative 5d and positive 5d are not the same thing. So I need to add something or subtract something from 5d in order to get negative 5d. And that's going to go in this diagonal box from 5d. If I fill in that box with negative 10d, then when I combine those like terms, I have negative 5d, which is that middle term. So now I repeat that process. To get what goes on the top of that column, I ask myself, what do I multiply by d to get negative 10d? And the answer is negative 10. So negative 10 times d is negative 10d, and negative 10 times negative 5 is a positive 50. So we're multiplying to fill in the box. We're adding the things that are inside. Now I need to extend my box because this 50 is not the term that I need. I need 41 for my constant term. So I need a box that's diagonal to this one. And I don't need the complete box. This is the last number that I'm going to need. And this is going to be my remainder. I know it's the remainder because I've divided as far as I can. I'm already on the last term, so I just have to make it right. What do I add to 50 to get positive 41? Well, I'm going to have to subtract 9. 50 minus 9 gives me a positive 41. That means that this number right here, this quotient, negative d minus 10, plus the remainder divided by the original denominator, that represents the remainder. So this is my answer. It's like when you have an improper fraction, say 7 over 5. You get a mixed number for that. 5 goes into 7 one time, and you have a remainder of 2. So that's plus 2, the remainder, divided by 5, because that's the thing you were originally dividing by. We don't usually write the plus sign when we have numbers. We just write that as a mixed number, 1 and 2/5. But for a polynomial, we need to add the fractional part, and that fraction comes from the remainder. Give this short practice a try. If you need more practice after this, then you can find some practice and explanations on IXL GG5 and IXL GG6. Those are not required, but if you work part of them, they might help you to work through these problems.